combination of this talk is supposed to be a combination of a introductory talk, and also I want to talk about, or at least point to two very recent papers. So we'll start with the introductory material. So lattice models arose in statistical mechanics. They're systems like structures of spins on lattices that are usually in the ones that we're interested in will usually be two-dimensional. And they potentially exhibit behavior such as phase transitions and scaling phenomena. So they first appeared in statistical mechanics. Certain models are called solvable, and the first example is the two-dimensional Ising model. It's possible to analyze that very precisely, and after some preliminary work, this was done by Onsager in 1944. And then the six-vertex model appeared. This was actually, had its origins in the theory of ice that was studied by Linus Pauling, but it was solved by Elliot Lieb and Bill Sutherland, and then Baxter introduced powerful methods that are also capable of solving the 8-vertex model. And these methods led to the theory of quantum groups. So I'm going to at least touch on that topic. Now, although lattice models first arose in statistical mechanics, they're also related to things that appear in quantum mechanics. Heisenberg's chains, for example. Through quantum groups, through the theory of quantum groups, they're connected to knot theory and potentially to topological quantum computing. So Belovin, Polyakov, and Zamolodchikov showed that the scaling properties of solvable models at a critical point, at a phase transition point, can be predicted by conformal theory. There's so this is quite an interesting fact. So then there's all kinds of connections with conformal field theory, but recently there have been some new areas where they appeared, and these are integrable probability and representations of p-adic groups, and also non-symmetric McDonald polynomials. So these could be, I guess I mentioned that I was going to focus on two recent papers, and these are represented in both of them. Okay, so I have to tell you what the six-vertex model is. And, it can be traced back to Linus Pauling's 1937 paper on ice. Linus Pauling was discovered interested in the fact that ice could appear in different configurations, and the six-vertex model would be one way of approaching two-dimensional ice. So the six-vertex model is called ice-type models. There's a corresponding phenomenon or there's a corresponding Hamiltonian in the Heisenberg spin chain called the XXY Hamiltonian. So if you can solve the six-vertex model, you can solve the XXY Hamiltonian. If you can understand the 8-vertex model, which Baxter did, then you understand the most general XYZ Heisenberg spin chain, most general assuming field free. So analysis of these situations and Baxter's work in particular, the Yang-Baxter equation, by Fadeev and his students. I'll mention Kulish, Skleonin, and Reshetikin. This led to the discovery of quantum groups, and this was put on solid footing by Drinfeld and independently by Jimbo in the 1980s. So the field-free six-vertex model I'm going to talk about, there's a powerful tool, the Yang-Baxter equation, and that's at the center of everything. So I want to explain what the Yang-Baxter equation is. So I'll start with a rectangular grid, and the grid could be infinite, or it could be finite and wrapped on a torus, or it could have values which are at the top, bottom, left, and right of the grid. So those are different possible boundary setups, and generally there are minor differences between the theory in these different cases. So if there are boundary edges, if the thing isn't infinite or somehow wrapped on a torus, then the spins of the boundary edges are going to be fixed. So the spin is a value which is, let's see, what's the colors here? I guess I'm using red for minus spins and blue for positive spins. So the boundary spins will be fixed, and then the spins of the interior edges are going to be allowed to vary. Are there any questions? So a state of would assign spins to all of the edges, and only 6 possible configurations at a vertex are allowed. And names for these are A1, A2, B1, B2, C1, and C2. There would be 2 other possible ones, which would be mirror images of C2. We could call those D1 and D2. If those appear, then we're in the 8-vertex model. But just the theory of the 6-vertex model is already extremely rich. Oops. I'm going to fix 6 numbers, which I guess in the statistical world would probably be non-negative real numbers. I'll call those A1, A2, B1, C1, and C2. And the idea is that at each vertex, you will have one of those 6 numbers, which is picked out by this table, and then you multiply all those numbers together. So you take the product over all the vertices, and that is the Boltzmann weight of the state. So Boltzmann weight of the state is the product of the Boltzmann weights of the adjacent vertices. And then if you sum over all states, you end up with a value which is called the partition function. Now in statistical mechanics, the probability of a given state is the Boltzmann weight of the state divided by the partition function. And in realistic models, this would be a non-negative real number. And of course, the sum of them is equal to 1. So this gives you a probability distribution on the set of states. So you can ask if 2 states are likely to be, well, you could ask yourself, for example, with this probability distribution in a typical state, are the values of the spins at one place correlated with the values of the spin at some remote place. And so you could have systems that are frozen, such that there are such correlations, or you can have systems which are unfrozen. And the Boltzmann weights and the partition control these questions. So the partition function is quite important. And it's also true that the partition function controls thermodynamic properties of the system, such as entropy and free energy and so forth. So Then I have a quick classification of some types of six-vertex models that are going to come up. The field-free models will be characterized by the fact that A1 is equal to A2, B1 equals B2, and C1 is equal to C2. And these were the examples that were solved by Lieb, Sutherland, and Baxter. I could mention also Korup and Izergin. And this was a key example in the discovery of quantum groups. The quantum group in this case is the quantized enveloping algebra UQ of SL2 hat. Q is a number that you can read off from the Boltzmann. This is quantum affine SL2. It's a quantum group. I'll say a little bit more about quantum groups later. Now, another class of examples would be where A1, A2 plus B1, and B2 equals C1, C2. If you had an 8-vertex model, you could say A1, A2 plus B1 plus B2 equals C1, C2 plus D1 plus D2. These are called free fermionic, and they contain the above example of UQ of SL2 hat, where Q is equal to -1, so that this number here, which is sometimes called delta, is equal to 0. But they also contain another quantum group, which is important for us, and this is this Lie superalgebra, UQ of, so it's a quantum deformation of a affine Lie superalgebra called GL11. And that's important in this talk. Also, stochastic models have been appearing in work of Borodin and his collaborators and students. So the stochastic models are characterized by the fact that A1 equals A2 equals 1, and B1 plus C2 is equal to 1, and B2 plus C1 is equal to 1. And if that's true, then you can think of the row transfer matrices as forming a Markov chain. So these are examples are useful in studying things like asymmetrical exclusion processes and so forth. So, okay, and then there are, in addition to the 6-vertex model, there are variants which I will call bosonic. So, so in the 6-vertex model, we allow minus spins to occur with multiplicity 1. But what if we allowed them to accumulate on an edge, especially a vertical edge? So I'm going to say that the at least the vertical edges here's a segment, could carry minus spins, but it could carry several of them. So if it carries n, I'll indicate that like that. And then you have these Boltzmann weights. If n is not allowed to be bigger than 1, then you're back in the 6-vertex model. So these are bosonic weights, and we can distinguish between bosonic weights and fermionic weights. And so far, the only example we've seen is a 6-vertex model. Okay, so the field-free 6-vertex model, as I mentioned, is this example that was studied by Baxter. So we have these Boltzmann weights, A1 equals A2, B1 equals B2, and so forth. And we have a parameter delta, which is going to be a function of a squared plus b squared minus c squared. It's basically the cosine of an angle of a triangle that has sides a, b, and c. And I want that to be, that's an important parameter. I'll explain why in a minute. So I want to study the row transformation. So let me explain what I mean by that. So if I consider a sequence of vertical edges, and I have spins assigned to those can be thought of as being picking out a basis vector in a vector space. Maybe, for example, in this example, I've labeled the columns from 0 up to 5, and I have minus spins in columns 1, 2, and 4. So I think of this as being living in some vector space, and I'll denote it by v sub 4, wedge v sub 2, wedge v sub 1. It might be the exterior power of a vector space with the exterior algebra of a vector space with basis vectors labeled from 0 to 5. And if you considered infinite grids, then you would be in the world of the fermionic box space. Now, then I can think, if we have a single row of ice, we can think of that we have two pieces of data. We have the spins above the ice, and we have the spins below the ice, and so we can think of this as being the product of the Boltzmann weights at these vertices. We can think of that as being an entry in a matrix, and that's the row transfer matrix. So, so if we consider this system with just a single row, its partition function can be thought of as being that you take this basis vector for the top row, you apply a linear transformation to it, and then you pick out the coefficient of the bottom row. And so you have an endomorphism of this vector space, and that's the row transfer matrix. So if I have rows, I would actually rather have R rows, but anyway, if I have n rows, and I have the row transfer matrices, and then I have vectors corresponding to the top and the bottom boundary conditions, then the partition function has this kind of interpretation. So I iterate the row transfer matrices. So now Baxter had some very good ideas. He realized that you should study the partition function by trying to diagonalize the row transfer matrices, and that a good way of doing this was to embed the row transfer matrices into a large commuting family. So, then, furthermore, he understood that there was a powerful tool for doing that, which was the, he called it the star triangle relation, but people called it the Yang-Baxter equation. The term star triangle relation, I think, goes back to Onsager, and so it didn't play a big role in Onsager's work on the Ising model, but it was present. So then we have this parameter which I call delta, and I want to make a row of n vertices using these values of A, B, and C. So I will have identical Boltzmann weights at all of these vertices, and I want to use toroidal boundary conditions. So I'm going to identify the left edge with the right edge, so that this row wraps around in a circle. Later, I want to consider systems when you don't do that, but that's the point of view that we'll take at the moment. And then Baxter proved that if you have two vertices, let's call them V and V prime, with weights A, B, and C, and A prime, B prime, and C prime, as long as these deltas are the same, then the row transfer matrices commute. And the way that he did it is sort of the archetype for everything, you know, representations of Hecke algebras and proving that things are symmetric functions. So this is what I want to explain this proof. So I have these vertices, and I'm going to have these rows of ice, and then there's a relationship which is called the Yang-Baxter equation. So it turns out, and this can be proved with a little bit of algebra, that there is another kind of vertex. Sorry, I don't know what I did, but I don't want to do it. Okay. I think I've discovered some feature of notability that I don't want to use. But anyway. So there's another type of vertex, and I'm going to draw it rotated, and I'm going to call it V double prime. And it has the property that for any edge spins, epsilon 1, epsilon 2, epsilon 3, 4, 5, and 6, that these two systems have the same partition function. So I am going to sum over the spins on the three interior edges, and I'm going to get a value. And then I do that for this one, and those are going to be the same. So you can write down an algebraic formula that expresses the Boltzmann weights for V double prime in terms of those for V and V double prime. I won't do that because we don't need it. We just need the existence of this vertex. And I'm going to call this vertex the R matrix. Are there any questions about what I've asserted? Okay, now I want to orient this vertex in a particular way. So I rotated it. I rotated it 40 from the previous vertices by 45 degrees. And did I want to rotate them clockwise or counterclockwise? I want to rotate them clockwise, I guess. And so I need a notation that will show that. And so I will draw this vertex as an overcrossing. There's another reason that we want to do that, which is that this is quite suggestive of one direction that your thinking can go, which is in the direction of knot theory and three-dimensional stuff. So anyway, I'll use, now I've drawn everything as an overcrossing and an undercrossing, and so I modify the pictures this way. I think if you look at this closely, there's a way to zoom in, right? Sorry. Let's do this. I've drawn this so that it has an obvious orientation, and I do that also for the R matrix. And now the picture looks like this, and you can actually see that this is starting to look like a braid, and these two braids are equivalent to in other words, these two pictures are actually equivalent in the braid group, that I can move these strands around, and this identity is true. So that's a possible way of remembering the Yang-Baxter equation. And I also need to know that the R matrix is invertible. So there's another kind of vertex which I'll draw this way, such that if I juxtapose these two vertices like this, now of course I'm summing over the interior edges, sum of the spins of the interior edges, and I'm going to get 1 if epsilon 1 is equal to epsilon 4 and epsilon 2 is equal to epsilon 3, otherwise I get 0. So I can say that the result of this diagram is the same as two straight lines. Okay, and then this is what Baxter did. So I want to show that the row transfer matrices commute. So I do this. I put delta, row of deltas on the top, and then the v vertices, and then the v prime vertices, and then the epsilons. And I want to show that I can switch the v's and the v primes. So I insert, and remember, everything wraps. So this goes around and comes back around here. So I insert this neutral braid. It's the R matrix and then its inverse. And then I start applying the Yang-Baxter equations. So each time I apply the Yang-Baxter equation, the V double prime, which is now here, is going to move across a strand, and it's going to switch V and V prime. And I repeat this. When I'm done, I remember that this ties back into here, so I can cancel it. And I've now got V prime and V double prime and V prime switched, and I've proven the commutativity of the row transfer matrices. So this was Baxter's brilliant idea, and the Yang-Baxter equation is the key to everything. Now, for non-toroidal boundary conditions, I want to be able to do something similar. So I'm going to put plus signs on the left edge and minus signs on the right edge. And then what you have is that the row transfer matrices don't commute, but they compute with the scalar. And the scalar, you can compute it very easily, is equal to this value. These are the A prime and the A double prime for the R matrix. Korup and Izergan were the first to study domain wall boundary conditions, and they showed in the examples they were studying that the partition function could be realized as a determinant. And so anyway, we're going to be in this situation. Okay, are there any questions?
Yes, I have one question actually. I thought that you said that the theorem that we're proving is that the t's commute in the case that the deltas are equal. Delta ABC is equal to delta A prime, B prime, C prime. But here you're saying that the constant is A2 divided by A1. Wouldn't that be equal to 1 then?
No, so actually, yes, except that I said I'm going to be considering more general examples. So I'm saying that I'm going to drop the field free condition that A1 double prime is equal to A2 double prime, because we'll encounter situations where they're not equal.
Okay, so this relation that is above works for more, like for any A6 weights?
It works when I need it to work. So we'll encounter examples where you use this.
Okay, thank you.
Okay. Okay, then I want to digress a little bit about quantum groups. The example of the Yang-Baxter equation that Baxter found what was explained by first of all, it was studied by the Fedayev's school, and particularly Kulish, Skleon, and Reshetikin constructed a quantum group. It's now the UQ of SL2 hat, which was then a key example in Drinfeld's theory of quantum groups, which is set out in his 1986 ICM talk and other papers that he wrote around the same time. So quantum groups are not groups, they're Hopf algebras, but they can be understood as deformations of Lie groups that you replace the Lie group by its quantized and by its enveloping algebra, and then you can deform it in the category of Hopf algebras. And quantum groups have a property that if you have two modules, then there is a isomorphism of modules. There's an element of H tensor H, and then tau is going to be the flip map. This has the property that if you apply R, and then you apply the flip map, that you end up with a mapping from V tensor W to W tensor V, which is actually a homomorphism. And this is the R matrix. Oops. So this is related to the vertex V double prime, which I introduced earlier. So anyway, it gives a braiding in the module category. So the module category becomes a braided monoidal category. I won't define that, but I'll give you an example of the implications. So, so I could go from U tensor V tensor W to W tensor V tensor U in two different ways. First, I could use the braiding to switch U and V. Then I could switch U and W, and then I could switch V and W. And I have a sequence of homomorphisms, which I've diagrammed on the left. And if I read these off from top to bottom, I get a picture that looks like this. Now, this probably looks somewhat familiar because you can imagine that there's a braid which is going on here. And these two braids are equivalent in the they're the same homomorphism from U tensor V tensor W to W tensor V tensor U. And this is the explanation of the Yang-Baxter equation. So if you unravel the consequences of this, this implies the Yang-Baxter equation as Baxter understood. So, so any three modules of a quantum group will give a solution to the Yang-Baxter equation like this. So in Baxter's example, the quantum group is called UQ of SL2 hat. So what is SL2 hat? The SL2 hat is a Lie algebra. It's a central extension of SL2. So actually, you make a central extension, and then you usually join a derivation. I didn't mention that, but anyway, it's a central extension of SL2. And because you have this center, there's a parameter that you can tune. So if you have a SL2 module, like the two-dimensional standard representation, and then you have a complex number, you produce a module, and oh, sorry, I got mixed up. What I wrote was wrong. I'm going to correct it. So I'm sorry. I wrote something which is incorrect. I'll just delete this. No, what you do is that you first take SL2, and then you pattern it up by adjoining the torus. So if you take a Lie algebra and then an associative algebra and you tensor them, then you can get a Lie algebra. And then you make a central extension. And this is what I meant to write. So this is where the parameter is that you can tune. Sorry, I wrote something which was wrong, but this is now correct. You can also adjoin the derivation and make it a little bit bigger, and that's sometimes important to do. So the Yang-Baxter equation now, I want to look at another example. So I'm going to impose the free fermionic condition. And then there's a parametrized Yang-Baxter equation that has a non-abelian parameter group. The parameter group is GL2 cross GL1. And this was actually found by Korepin, and with Brubaker and Friedberg, we rediscovered this fact, and it wasn't until we'd actually already published our paper that Reshetkin pointed out to us that that Korepin had done this earlier. So unfortunately, we don't acknowledge in the paper. Anyway, this is a pretty big group. It contains some one-dimensional groups. This here can be thought of as being the Hopf algebra of functions on GL1, and so there's a GL1 in there, and that explains this. And then there's another piece which is related to this this other quantum group. This is a Lie superalgebra, which has been quantized, and it's been affinized and then quantized, and this plays an important role in everything. Questions? Okay, I'm going to talk about something called Tokiyama lattice. The name Tokiyama is underlined in red here because Notability thinks I misspelled it. But anyway, I spectral parameters, which we'll call Z1 up to Zn, and then we have the Schur function, Schur polynomial. This can be thought of as being a character of the group GLRC. If you take a Schur polynomial, fix a partition, take the Schur polynomial, plug in the eigenvalues of an element of GLRC, you get a value, and that's a character of an irreducible representation. So what I want to do is I want to define a system whose partition function is this. Schur function, and then it's a deformation of the Weyl denominator. We're going to multiply by it. So if you think of this in Lie theoretic terms, this is a product over the positive roots of GLR. Tokiyama himself didn't consider the ICE model, but he considered a equivalent algebraic setup in which he had a deformation of the Weyl character formula in which this value was expressed as a sum over Gelfand-Zetlin patterns, and those that can be related to this setup. Then Hamel and King noticed that you could take Tokiyama's theorem and reformulate it in terms of lattice models, and Brubaker, Bump, and Friedberg showed that you could then introduce the Yang-Baxter equation. So the partition lambda is going to be encoded in these boundary conditions. So the here that there's going to be some minus signs up here, and those control the partition lambda. In this example, the partition lambda is 330. We're going to add 210 to make those values distinct, and then we're going to put minus signs in there, and we'll put more minus signs on the right edge. And then the claim is that if we use these Boltzmann weights, which are related to this Lie superalgebra, that the partition function is equal to what I said that it was. Okay. Now, then I want to talk for a minute about Whittaker functions. So I want to be a local field. It could be the p-adics or the real numbers. I'm going to consider representations of this group GLRF. That's non-compact and it has infinite dimensional representations. Most of the representations are dimensional. And if you have a representation, maybe I should say an irreducible representation, then there exists at most one linear functional that has this transformation property. So I'm going to take an additive character of F, and then if I have a lower triangular matrix that I'm going to have a character of that group, and this functional is supposed to transform by that character. This is called a Whittaker functional, and it's unique. Then if I have a vector in the group, then I can consider this function. Then I'm going to apply the representation to the vector, and then I'm going to apply this functional. This is called a Whittaker function. And for the reason it's called a Whittaker function is that for GL2R, these are confluence hypergeometric, which were called studied by Whittaker. There's a chapter on the confluence geometric function in Whittaker and Watson. But we're interested in the non-Archimedean case. And then there's a formula of Castleman and Shalaika, which would say that if I take the spherical Whittaker function, the spherical vector is a particular vector which is fixed by maximal compact subgroup. So the maximal compact, no. Okay. Here's the maximal compact subgroup. This has a unique up to scalar fixed vector in an irreducible representation. It's a Gelfand subgroup. And if you take that vector, the corresponding Whittaker function has values which are given exactly by the Tokiyama formula. So we have lattice models that represent this value of the Whittaker function. And then the whole plan is to try to emulate more interesting Whittaker functions. And as the Whittaker functions become more interesting, the lattice models whose partitions functions are equal to this become more interesting. And eventually you end up with a rather rich theory. So in order to get Whittaker functions that are fixed by deeper level subgroups, we need to introduce colored models. Now, these were introduced by Borodin and Wheeler. Possibly they were introduced by other people, but they came to our attention through the work of Borodin and Wheeler. There's two theories. There's a bosonic theory, and then there's a fermionic theory. And I understand it in the bosonic theory, the relevant quantum group is UQ of SLR plus 1 hat. And in the fermionic theory, the quantum group is this Lie superalgebra. And so we're going to consider lattice models that are related to these. These are going to represent Whittaker functions that are invariant under the Iwahori subgroup. There's now going to be R factorial goes. R factorial is the order of the Weil group. They can be related to each other by certain recursion relations. There's one that's simple, and then others are obtained from that by applying some operators, which are called Demeser-Whittaker operators. I write those down in a later slide, which I think I'll be able to get to. So in the colored models, the horizontal edges correspond to the R+1 dimensional standard modules of this quantum group. So the standard module is a super vector space. It has an even part that's r-dimensional, and then it has an odd part that is going to be one-dimensional. In terms of the colors, the even part corresponds to the R colors, and then the odd part. Oh, I intended to replace this slide. Never mind. Yeah, I made a different picture for this, which this, I'm sorry. I won't try to fix it, but I don't want there to be repetitions of colors. So what I really want is this to be green. And this one can be green. 3 distinct colors. So the idea is that we have these lattice models. We have Boltzmann weights, and we have partition functions, and they exactly represent the values of these. The lattice models represent the values of these Iwahori Whittaker functions. So you might wonder what the Demeser Whittaker recursions are. They're obtained by applying these Demeser-like operators. They're divided difference operators. They're given by this formula. So f is going to be some function of the spectral parameters. I subtract f of, apply a simple reflection, then I divide by something. This is guaranteed to be divisible by this, and so is this other term. So we have these operators. They're similar to what's called Demeser-Lustig operators that also are fairly well known. They satisfy a Hecke relation, and they satisfy braid relations, which I didn't mention, and they give recursions that express these Whittaker functions in terms of simpler Whittaker functions. Now, the punchline is that these correspond to the Yang-Baxter equation. So so the information that you get out of the Yang-Baxter equation is that these partition functions also satisfy these Whittaker recursions, and that is how we're able to prove the theorem. So the theorem says, well, if you take G, you have some freedom to choose it. You can translate it by the Iwahori subgroup, translate it by the by this unipotent subgroup that the Whittaker function has a transition property for. So you can if you want to know all Whittaker functions, you can choose G from this set, and then there's a lattice model whose partition function is equal to this value. And you prove this by using Yang-Baxter equation to prove Demeser recursions, and then you use methods of representation theory, intertwining operators, and so forth, in order to prove the Demeser recursions for the Whittaker function. You compare; they're the same, and you prove this theorem. This is what the Boltzmann weights look like. So there's actually there's more possibilities for the Boltzmann weights. These are the ones in which there are no edges that carry more than one color, but we actually allow edges to carry 2 colors, and in fact, they can carry as many colors as you want, but they can never carry a color with multiplicity greater than 1. So these models are fermionic. And here are 2 more interesting states. So in the first state, you have 2 edges which cross, And then they could cross again, so there would be another state that I didn't try to draw. And in the second one, you have an edge which carries two different colors. Actually, a lot of very rich things can happen. So you encode, you use the top boundary data to encode the group element, and then you use the right boundary data to encode a Weil group element, and the Weil group element indexes the Whittaker function. Are there any questions? Okay, now lattice models related to this more sophisticated quantum group, UQ of hat Rn, appeared within the last 3 weeks. So two papers were posted on the archive within a few days of each other. One was by us, and the other one was by Aggarwal, Borodin, and Wheeler. And they both have models for this quantum group, which may be very closely related to each other. It's not certain that they're the same thing, but they're very close. So for us, the application is to Whittaker functions on so-called groups. So the metaplectic group is a central extension now of GOR. You make a central extension by a group of roots of unity. Assume that the local field has enough roots of unity, and then you have models which represent these Whittaker functions, and so we need R distinct colors, but we also need distinct supercolors or S colors. So the Yang-Baxter, the form of the Yang-Baxter equation tells us what the quantum group is, and then when we look at the models, we see these colors and supercolors. So they could be thought of as being like gravitons and gravitinos. They're things that belong to each other. Supersymmetric pairs, and the color and the S color can occur together on the vertical edges. So and then you can make colored lines as before, and the colored lines as before start at the top and they end up at the right edge. But the S colored lines, colored end lines, end up at the left edge. And in the models that we're considering, we're going to take the colors to be distinct, but the supercolors actually could repeat on the left edge. We would allow that. Okay, so here's the scheme. So the principal series representations of this p-adic group have this metaplectic group have, as before, R factorial Iwahori Whittaker vectors, and they have n to the R Whittaker functionals. So that means that we would have n to the R times R factorial different functions that you want to evaluate, and you want to know the values at every group element. So we have data that encodes G, those go on the right edge. We have data that encodes the Iwahori vector, those on the right edge, and there's data that encodes the Whittaker functional, those go on the left edge, and for those we allow repetitions. And the miracle works, so there's Demzer-Whittaker operators. They're now rather complicated. They were first studied Pushkas and Patnaik, although precursors go back in the literature to other papers and so forth. So, but anyway, we make use of those to get Demzer recursions, and then we prove that these lattice models satisfy the same recursions. And that's my last slide.
Okay, thank you so much. for your talk. And I think now we can ask a couple of questions before going to the application Gather Town, where we could keep chatting for those who want to chat more.
You also want to try to figure out what's happening next week, right?
Yeah, especially if you want to give a talk about the representations of p-adic groups in relation to solvable lattice models, please write me. We're making the list of speakers, and this is really important. Do you have any questions? Okay, then I send the link in the chat of the Gather Town. So feel free to jump there, and see you next week.